Okay, so in the last lecture we saw the definition of LP spaces. So, these were functions which were whose pth power was integrable, and we also saw some inequalities, Holder's inequality and Minkowski's inequality. I will briefly recall them before we go ahead. Our aim today would be to prove that the LP spaces as a metric space. So, remember the LP norm gives you a metric space which makes it into a complete metric space. That is what we want to do now. So, recall that the space of functions which we consider are equivalence classes. In fact, functions which are equal almost everywhere are thought of as same functions in the space LP. For most of the computations this does not matter, but this is a point one should remember all the time. Okay, so, let us start. So, recall that we have LP spaces. So, as usual we have a space X, a sigma algebra F and a measure mu. So, this is our measure space, and on this we defined LP spaces. So, we generally denote it by LP of mu, which is all measurable complex valued functions such that the integral of mod f to the p d mu is finite. So, we looked at only p between 1 and infinity, and when p equal to infinity. So, this definition is for p strictly less than infinity. When p is equal to infinity, we had L infinity of mu. So, this was all those functions which are essentially bounded. So, that is a word which I did not use last time. So, let me define this. F is essentially bounded, which means that is there exists some m strictly less than infinity such that mod f is less than or equal to m almost everywhere. So, there may be a set which has measure 0 where this inequality is not true, but that we can discard, which. So, this also gives me the norm. So, let us start with here LP norm of the function f in LP. If I take the LP norm of f is defined to be. So, we use this simple which is integral over x mod f to the p d mu to the 1 by p. So, remember when we talk about the norm, there is always a 1 by p at the top, which is what makes it into a norm. Okay. So, when p is infinity, L infinity norm, well, how is this done? So, you look at all those m. So, you look at the infimum of things which are bigger than m, right. So, infimum of all those m such that mod f is less than or equal to m almost everywhere. So, this would be the smallest number which satisfies. So, in particular which will be this will be used every now and then, mod f is less than or equal to L infinity norm of f almost everywhere, right. This is a constant, the L infinity norm, and as a function f will be bounded by L infinity norm of f almost everywhere. Okay. So, this also tells me that if I look at the set x such that mod f of x is strictly greater than L infinity norm of f, okay, this will have measure 0. So, mu of this will be 0, because you can't have a positive set of positive measure where mod f is greater than this quantity. So, this is the space we are looking at. Also recall that we identify functions which are equal almost everywhere, right. Functions which are almost equal almost everywhere. In other words, the space is a collection of. So, LP mu for 1 less than or equal to p less than or equal to infinity is the collection of equivalence classes of f. d mu is finite, right. The norm does not change, right. If I take f and g in the same equivalence class, then f equal to g almost everywhere, and so the norm does not change. So, integral over mod x mod f to the p d mu is same as integral over x mod g to the p d mu. So, the norm will not change whatever representative of f we take from the equivalence class. Okay. So, in this space we define the distance function d. So, I take 2 points. Well, strictly speaking I should take equivalence classes. So, let me do that. I will drop the equivalence class after some time, and once you are used to it, it does not really make any serious difference. So, if I take 2 points in the space which are 2 equivalence classes, their difference is defined, the distance is defined to be integral of mod f minus g to the p d mu to the 1 by p. So, again it is easy to see that this is well defined because of this, whatever instead of f and g, if I take f1 from this class and g1 from this class, I can use f1 and g1 in the definition of the distance, and I will still get the same quantity because of this. Okay. All right. So, that defines a distance function, and d is a metric. So, LP mu with d is a metric space. Okay. So, this we had checked last time. So, that is where the equivalence classes come in. dfg equal to 0 implies f equal to g almost everywhere, and that is what forced us the equivalence class property. So, now we want to prove that. So, this is the main theorem. So, let me get, so LP is a metric space, with the distance function d. Okay. So, let me write the main theorem. One of the most important properties of LP spaces is that LP mu is a complete metric space, with of course, the distance function dfg. So, I am dropping the equivalence class now, dfg to be integral over x mod f minus g to the p d mu to the 1 by p, right. With this, with respect to this metric, LP mu is a complete metric space. So, let us do the proof, and then we will look at more properties of LP and some examples as well. Okay, proof. So, first assume, so in many of those you will see that L infinity case is easier to do. So, assume that 1 is less than equal to p, strictly less than infinity. Well, what do you mean by a complete metric space? I need to show that if I take every Cauchy sequence converges, every Cauchy sequence converges in LP, of course, it converges to something in LP. So, that is what we want to prove. So, let us take a Cauchy sequence. So, let Fn be a Cauchy sequence. Fn. So, strictly speaking one should take the equivalence class, but as I said it does not really matter. Let Fn be a Cauchy sequence in LP of mu. What do I want to show? So, need to show that there exists f in LP such that the sequence Fn, which is the sequence in LP, converges to f in LP. So, this is important, it has to converge in the given metric space, not in some other space. So, I need to find a limit of Fn which is the limit of Fn's in that metric space. Okay. So, Fn is Cauchy. What does that mean? So, Fn Cauchy. So, let us write down the definition of that. Fn Cauchy implies for every epsilon positive there exists some capital N such that the distance between Fn small fn, f small n and f small m will be less than epsilon for every n and m strictly greater than capital N, right. After some stage you should be able to reduce the distance. But remember, the distance is defined in terms of the LP norm. What does this mean? This means the LP norm of Fn minus Fm, right. This is less than epsilon. Okay, so remember, this is also given by the integral of mod Fn minus Fm to the p d mu to the 1 by p, right. This is what is less than epsilon is for every n and m greater than capital N. Okay, so what we do is we choose epsilon to be 1 by 2 to the I. So, choose epsilon to be 1 by 2 to the I equal to maybe 1, 2, 3 and so on. So, epsilon depending on the value of epsilon we should be able to get capital N, so that beyond capital N we will have this inequality, right. So, that immediately tells us that we get a subsequence, f n I. Okay, so, I equal to 1, 2, 3 etcetera, such that norm of f n I plus 1 minus f n I, right. This is the distance between f n I plus 1 and f n I. This is, so this will come from the given subsequence f n, right, less than 1 by 2 to the I. Okay, you will see why we are doing this, I equal to 1, 2, 3 etcetera. Well, what exactly did we do? So, let us take some metric space. Suppose I have some sequence y n which is Cauchy. Okay. Then I can choose epsilons to be 1 by 2 to the I and I will get some number. So, I have y 1, y 2, this is the sequence y 3 etcetera, right. So, at some point let us say y n 1, from here onwards distance will be less than or equal to 1 by 2. So, I have y n 1, then I take epsilon to be 1 by 2 to the 2. So, I will have to go further and I will get y n 2. So, that is the n 2th place. After that it would be any 2 points will have distance less than 1 by 2. So, that I call y n 2 and so on. So, this is how the subsequence is chosen. So, this is the subsequence of the original sequence with the extra property that the distance is very small. Okay. What is the advantage of doing this? These are functions, right, and these are, we are looking at the LP norms of these functions. Okay. So, because they are functions we define new functions. So, define let us say g of k, g sub k, this is a function defined by summation I equal to 1 to k f n I plus 1 minus f n I modulus. Okay. Well, what does this mean? This means that g k at x is, you look at f n I plus 1 at x minus f n I, right. So, x and x. So, this is how the function is defined. And we take another function. So, let us take the infinite sum. So, g of x to be the sum I equal to 1 to infinity. So, that is just k going to infinity, right, mod f n I plus 1 x minus f n I x. Okay. So, g, what is g? So, g is simply the limit of g k's. So, g k, well, it is not just simply the limit because you are adding positive numbers. So, g k increases to g, right, for every x. Well, it may converge to infinity, but these are positive numbers. So, there is no problem in talking about the limit. Now, let us apply Minkowski's inequality here. So, apply apply Minkowski's inequality to GK. So, remember what is Minkowski's inequality? If I have two functions, let us say f1 and f2, I add them and look at the LP norm, that will be less than or equal to LP norm of f1 plus LP norm of f2. Of course, this you can extend it to finitely many, right. If I take 3 functions f1 plus f2 plus f3, then by the previous step we have this is less than or equal to f1 plus f2 and then you take the LP norm plus f3's LP norm, right, which is of course less than or equal to, because here we can apply Minkowski's again. So, we will get L1 norm of LP norm of f plus LP norm of f2 plus LP norm of f3. So, I can do this finitely many times. So, I will get if I look at the LP norm of GK. So, LP norm of GK is less than or equal to LP norm of I equal to 1 to. So, let us go back to the definition of GK. So, we are looking at I equal to 1 to k. The LP norm of f ni plus 1 minus f ni, right, that is the function there. So, I take the LP norm. Okay. So, this is simply Minkowski's inequality, but this is less than or equal to summation I equal to 1 to k 1 by 2 to the I, right. That is how we have chosen the subsequence which is less than or equal to 1. Okay. So, this is true for every k. So, whatever finite sum you take, that is bound, the LP norm is bounded by 1. So, this allows us to estimate the norm of G as well. So, what is G? So, remember G is the infinite sum, right. G is I equal to 1 to infinity mod f ni plus 1 minus f ni, okay. And we know that Gk increases to G. So, Gk to the p will also increase to Gk to the p is greater than or equal to 1. So, there is no problem here, and so by monotone convergence theorem, so these are all positive functions. So, there is no, we do not have to take the modulus. By monotone convergence theorem, Gk to the p d mu will increase to G to the p d mu, right. That is monotone convergence theorem, because Gk increases to G. But what about this? These are less than or equal to 1, right, because that is the pth power of the LP norm of Gk, that is less than or equal to 1. So, in particular limit also will be less than or equal to 1. So, this implies integral over x G to the p d mu, G remember is a positive function, is less than or equal to 1. So, that is same as saying, so that implies in particular, so G will be in LP. So, in particular G is finite almost everywhere. So, hence we get that G is finite almost everywhere. G is finite almost everywhere mu, right, because pth power of G is integrable. So, it can't be infinity on a set of positive measure. Anything which is integrable has to be finite almost everywhere. Well, what does that mean? This means that, so this tells me that if I look at G, which is the infinite sum I equal to 1 to infinity mod f ni plus 1 minus f ni, right. So, this I put an x here is finite, that means the series converges almost everywhere mu, right. So, that means there exists some set which has measure 0. So, let us say there exists E such that mu of E equal to 0 and x in E complement implies this converges. So, that is what it means. Well, what is the consequence of that? So, you can define. So, let us take the modulus out of Gk. So, let's write it down again. So, G sub k is simply summation I equal to 1 to k mod Fni plus 1 minus Fni. Okay. So, if I take the modulus out of this, then I am adding. So, I equal to 1 will give me Fn2 minus Fn1, right, plus Fn3 minus Fn2. So, this is what is known as a telescoping sum dot 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 plus Fn k plus 1 minus Fnk, right. So, maybe I should write one more term. So, let us dot 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 plus Fni, so Fn k minus 1 minus Fnk plus Fnk plus 1 minus Fnk. Okay, so I made a slight mistake. So, let us get this one correct. This is Fnk and this is Fnk minus 1, right, Fnk plus 1 and Fnk. Yeah. So, this is how it looks like if I take the modulus outside, and you see that this cancels with this will cancel with this, etc., etc., right. So, except this, everything else will get cancelled and the last term, right. But if I put the modulus, I know this converges. So, in particular without the modulus it has to converge, because of absolute convergence implies conditional convergence. So, what we get is, if I look at Fn1, okay, minus okay, or minus Fn plus 1 plus, okay. So, Fn2 minus Fn1 plus Fn3 minus Fn2 plus, etc., etc., plus Fnk minus Fnk minus 1 plus the last term in Gk Nk plus 1 minus Fnk. If I look at this, well, what will happen? I know, because so I have only added this, which is a fixed function. Okay. So, this does not affect the convergence. So, it is a fixed function which I have added. Well, this is nothing but, well, this cancels with okay. So, maybe I should put a plus here. This cancels with this and this cancels with this, etc., etc. Telescoping sum, only the last term will remain, this and this gets cancelled, and I will have Fnk plus 1, Fnk plus 1, right. But the left hand side, as k goes to infinity, is supposed to converge. So, that is same as saying the limit of Fnk will exist, right. Okay. So, this implies that limit of k going to infinity Fnk. So, this is the exist for every x in E complement. Remember, we had a set E where measure was 0 and outside which this converged, and wherever this converges absolutely, it will converge conditionally, and for those points we have this limit existing. But Fnk, remember, Fnk is the subsequence of the original sequence, is a subsequence of the original sequence, Okay. So, what we have found is, we have found a function f as a limit. Okay. So, define f of x to be, okay. So, limit k going to infinity Fnk x. So, we know that this exists if x is outside that set of measure 0. Okay. On E which has measure 0, you can put 0 or 1, any number, does not matter, because mu of E is 0, the measure of E is 0. Okay. Yeah. But let us put a constant, because we do not know if the sigma algebra is complete. So, if we arbitrarily define, it may not be measurable. Okay. But with this definition, f is measurable, and Fnk converges to f almost everywhere. Okay. So, we have found a limit. Okay. But this does not prove anything. So, we need to show two things. Okay. We need to we need to show 2 points. Well, what are the 2 points? 1, f belongs to LP, okay. 2, Fn converges to f, Fn is the original sequence in LP, okay. These are different statements. Here what we have is a point wise limit, right. So, this is a point wise limit. For each x we have some limit, right. So, point wise limit. That does not prove any of these statements 1 and 2, okay, but it is not difficult now. We have got a candidate, we will just show that our sequence converges there. Okay. So, now apply Cauchy property again. So, apply Cauchy property again to Fn. Fn is a Cauchy sequence, right, we started with that. Okay. So, given epsilon I have some n, right. So, given, so let us take some epsilon positive, there exists some capital N such that whenever these guys n and m are greater than capital N, we have the LP norm. So, I will write this in the integral form, mod Fn minus Fm to the p d mu to the 1 by p, right. So, that is less than or equal to epsilon to the p, right. So, instead of 1 by p I have put epsilon to the p. So, this is true whenever this happens, okay. So, whenever this happens, this is true. Now, the nks are subsequence of the given sequence we have constructed, right. So, you see 1, 2, 3 etc. we have capital N here and we have numbers here. So, whenever this happens we have this. So, in particular whenever nk is greater than n, I know this happens, okay. So, let us fix m. So, fix small m strictly greater than n and let nk go to infinity in integral over x mod f n k minus f m to the p d mu. We can do that, right, because if n k goes to infinity it is going to be bigger than capital N and so this will be, this quantity will be smaller than epsilon, right. So, this will be smaller than epsilon to the p if n k is greater than capital N. But then what happens with limit? Let us apply Fatou's lemma there. So, apply Fatou's lemma, What does Fatou's lemma say? Integral lim_inf is less than or equal to lim_inf of integral. So, integral over x lim_inf integral lim_inf, right. So, with respect to n k is what I am taking f n k minus f m. F m is sort of fixed, right, but large enough, d mu m is large enough. This is less than or equal to lim_inf of the integrals. So, lim_inf of the integrals of, so mod f n k minus f m to the p d mu, right. But I know because of this is less than or equal to epsilon to the p, right. So, the whole thing is less than or equal to epsilon to the p, but what happens to the left hand side? I know what happens to f n k. F n k will converge to f, right, f we have defined here. So, f n k converges to f almost everywhere. So, the set E has measure 0. So, we will forget that. So, the left hand side becomes integral over x mod f minus f m to the p d mu. So, this proves both the things we want in one go, because this tells me epsilon to the p is a small number, okay. But what does it tell me? It tells me that f minus f m, it is a measurable function that is in LP, okay. So, f m minus f minus f m, okay, that will also be in LP because it is a difference of 2 LP functions, right. So, minus of this also should be in LP, okay. Well, so I should yeah, okay, I made it unnecessarily complicated. So, Fm is in LP, F minus Fm is in LP. So, if I simply add them, that will do, right, that is this is equal to F, that will be in LP. So, that was one of the things we wanted to prove. We needed remember two things. So, one of them is done, but I need to show Fn goes to F in LP. Okay. Well, so let us apply this again here. What did we get? From here we got this. This tells me that LP norm of F minus Fm is less than or equal to epsilon. Remember, when we take LP norm, there is a 1 by p, that is why epsilon to the p became epsilon for every n, every m greater than capital N, right. So, that is how we started with. Let us go back here again. For every n and m we had this, and this is where we changed n to nk and took the limit. So, for every small m greater than capital M n we have this, which is same as saying Fm converges to F in LP, right. So, this implies Fm converges to F in the LP metric, right, that is very important, LP. So, that proves that F is that proves that LP is complete. Okay. So, LP mu is complete, but we assume that 1 is less than or equal to p, strictly less than infinity. So, let us quickly get rid of p equal to infinity as well. So, assume p equal to infinity. Okay. So, let a k to be the set x in x such that mod f k x is strictly greater than the L infinity norm of f k. So, then of course, mu of a k will be 0. And also B m n. So, again it is not very difficult to see what is going to happen. We are trying to get rid of the problematic sets, but all of them will have measure 0. Okay. So, f n x minus f m x is strictly greater than the L infinity norm of f n and f m, and of course, this will also have measure 0 because of the definition of the L infinity norm. Now, outside, so you take the union of these sets, well in fact the union a k union of B m n. Okay. So, I will put m equal to 1, n equal to 1 to infinity, k equal to 1 to infinity. This is a countable union of sets of measure 0. So, E will also have measure 0. Okay. Well, what will happen outside E? So, in E complement, so recall that f n is a Cauchy, f n is Cauchy in L infinity. F n is Cauchy in L infinity, right. We are looking at p equal to infinity case. What does that mean? For every epsilon positive, there exists some capital N such that whenever small n and small m are greater than capital N, the norm, which is the L infinity norm now, f n minus f m L infinity norm is less than epsilon, right. So, that is like uniformly Cauchy. So, if you have for each x, if you have f n x to be Cauchy, it will converge because complex plane is complete, and that will do. So, apply that on E complement, you will prove that. So, this is something you can check, f n converges uniformly to a bounded function. Boundedness is very easy because all the f n's are bounded by some fixed quantity, right, because of this. So, if I look at this, I know that norm of f n minus f n L infinity norm is less than epsilon. So, because of that, L infinity norm of f n will be less than or equal to L infinity norm of capital F n plus epsilon. So, you take some epsilon, you will have this. This is true for every n, right, for every n greater than capital N. So, all of them are bounded. So, if I take the limit, that will also be bounded by this fixed constant. So, I will get a bounded function. So, outside E I know f n converges to f. So, f n converges to a bounded function, let us call that f in L infinity. Okay. So, we will stop here. We just proved that the spaces we were looking at L p of mu is complete as long as p is between including 1 and infinity. We will look at finer properties of LP spaces. For example, we know there are simple functions in LP spaces, there are also continuous functions with compact support and so on. So, we will look at such finer properties in the next lecture. Okay.